Okay, now we will discuss how to find local maxes and mins and absolute maxes and mins. First, we'll take a definition. F has a local maximum at the point AB if f of xy is smaller than that value for all points in an open circle centered at AB. And if f of xy is greater than or equal to f of AB for the same circle, then if all the other points are bigger than the f of AB value, then AB is a local minimum. Their absolute max or min, if the above holds, for all xy, all the points in the domain of F. Okay, let's talk about critical points. AB is a critical point if the partial of f with respect to x is equal to 0, and, okay, that's an and, partial with respect to y is equal to 0, or at least one of these partials does not exist. Okay, and then we have a theorem that says if f has a local max or min, at AB, then AB is a critical point. Notice it's not the other way around, and this is the same in the two-dimensional case. Just because it's a critical point doesn't mean it's a max or a min. So that's really an important thing to mention. Not every critical point is a local max or min. So what you have to do is you have to find the critical points, just like in two dimensions, and you have to test them. To make sure they're a max or a min. So let's get an example. We take the partials. These are easy in this case. And if we set them equal to 0, we get x equal to 0, y equal to 0. So that gives us the point 0, 0. Now that's a critical point. These are never undefined, so we don't worry about that. So f of 0, 0, which equals 1, let's see if it's a max or a min. Well, our function is equal to 1 plus x squared plus y squared. But that's always bigger than 1, which is our value of f of 0, 0. So we know that for all points, the values are larger than the value at the critical point. So that implies by the definition that f of 0, 0 is a min since everything else is larger. But just because it's a critical point doesn't mean that it's a max or a min. Let's look at this example and that'll show us that. We set m equal to 0, you get the point 0, 0. You get x equals 0, y equals 0. So that's our critical point. Now let's see what we can do with this. If y is not 0 and x is 0, then f of 0y is y squared, which is always positive. And if x is not 0 and y is 0, then we have f of x 0, which is minus x squared. And since it's squared and negative, that's always less than 0. So every circle around 0, 0 contains values greater than f of 0, since this is f of 0, 0, and that's f of 0, 0. F of 0, 0, if you plug it in, is 0. So we have values here, f's greater than f of 0, 0, and we have f of x 0 values less than f of 0 at the same time. And values less than f of 0, 0. So there's no local max or min. Let's graph this, see what happens at 0, 0. So let's switch to Maple. Over here. Okay, we want with plots. And we want to plot 3D y squared minus x squared. Let's just go from negative 2 to 2 because we only care about around 0. And if we box the axis, we can spin it around. And see at 0, 0, you have a saddle point that looks like a saddle. So we call that a saddle point. We have values of f above it right here, and we have values below it underneath at the same point around 0, 0 right here. So this is called a saddle point. Let's go back to our discussion. So just because it's a critical point doesn't mean that it's a max or min. That's a really important fact, and that's something that we learn in Calculus 1 in the two-dimensional case. So here's another test that we're going to use. Sometimes this is real difficult to use, but it works. F is a function of two variables with continuous second partials on a circle centered at the point AB. F of x AB is equal to 0, and so is f of y AB. We're going to define D to be the second partial at AB times second partial with respect to y at AB I'm going to square that. Okay, f of AB is a local min if D is greater than 0 and the second partial with respect to x of AB is positive. It's a local max if D is greater than 0 but the second partial with respect to x is less than 0. And if D is less than 0, it's a saddle point, so it's neither max or min. And if D is equal to 0, there's no information. Now notice that D is equal to the determinant of fxx, fxy, fyx, and f of yy, because f of xy is equal to f of yx, because you have continuous second partial derivatives. So this is another way that you might want to remember what D is equal to. Now D doesn't stand for derivative. D is this equation here, which can also be written as the determinant here. Okay, let's look at another example. Here's my function. And the partial with respect to x. Set these equal to 0. What I'm going to do is multiply this first one by 2 so the x's drop out. And then what we get is 3y squared minus 8y plus 4 equals 0. And that factors. So we get y equal 2/3 and 2. And then from first equation, we get x, 2x equal 4y, or x equal 2y. So when y is 2/3, we get x equal 4/3. And when y is 2, we get x equal to 4. So we have the point 4/3, 2/3, and 4, 2. These are our critical points. So let me call this A and let me call this B. Okay, when we take the second partial, so we get 2, 6y, and negative 4. So D is 2 times 6y minus 4 minus the minus 4 squared, negative 4 squared, so that's 12y minus 16. And D evaluated at the first point, because we plug in 2/3, is negative 8, and D evaluated at the second point is 8. So when D is negative, that's not an extrema as a saddle point, so A is a saddle point. When it's positive, then we check f of x. Well, here f of x is 2, so that's greater than 0. So this is a local min. B is a local min, and A is a saddle point. So it's easy to use a second derivative test sometimes. Okay, let's do few more definitions. This is for absolute max and min. And this is, we're going to have a bounded set. Okay, definition, couple definitions. A closed set is one that contains all of its boundary points. And a bounded set is a set that can be contained in some disk. So we have the extreme value theorem. If f is continuous on a closed and bounded set, then f attains an absolute max and min somewhere in D. Somewhere in D or on D. Okay, and the absolute extrema, which is the max and the min, are either critical points or boundary points. When we plug it into the function, the largest value is the maximum value, is the absolute maximum value, and the smallest is the absolute minimum value. So what we're going to do is we're going to find all the boundary points, all the critical points, and critical points in this case might be on the boundary, and then the largest value is the absolute max, and the smallest value is the absolute min. So we have absolute values when we're on a bounded set. So for an example here, we're going to do this function, the same one we just looked at, but it's bounded by a triangle with vertices -1, 1, 7, -1, and 7, 7. So it looks like that. Okay, we already know local min is at 4, 2. That was a previous example. We did that. That was a local min. So that's the example we just finished doing. Now we have to check the boundaries. So let's say this is boundary 1, this is boundary 2, this is boundary 3. So we have to check all these boundary points. So we have to check f of -1, 1, f of 7, -1, and f of 7, 7. Let's see. Okay, this is 72 if I plugged it in the function. This is 224. -1, 1, that's going to be 10. Okay, on boundary 1, the equation of boundary 1 is y equal -1. So we have f x negative 1, okay, let's go back and look at what f of x is. F of x negative 1 is going to be x squared plus 4x minus 1 minus 4, which is x squared plus 4x minus 5 on minus 1, 7. So we take the derivative of that. That's 2x plus 4. That gives us x equal negative 2. But x equal negative 2 is not in there, so we don't have to worry about anything being on that boundary. We just have to check the endpoints. Boundary to the equation is x equals 7, so we have f of 7y, and that is 49 minus 28y plus y cubed plus 4y, which is y cubed minus 24y plus 49. And this time y runs from negative 1 to 7. This is x in there. Okay, so f prime here is 3y squared minus 24. Set that equal to 0. Factor out a 3. We get y equal plus 2 squared root of 2 and negative 2 squared root of 2, but that's not in the domain. So if we check the second derivative, that's 6y, which is positive when we plug the y in. So this is a local min. So f7 2 squared root of 2 is a local min. We're trying to find the absolute min, but it may be, so we have to check it. Okay, on boundary 3, that equation, if you want to do it, it goes through 7, 7, and negative 1, so it's y equal x. So f of x is x cubed minus 3x squared plus 4x. F prime is, and if you solve that, that doesn't have any real roots. They're complex, so that's never 0, so there's no critical points we have to worry about there. Okay, so let's get all the points that we've seen. Those are our boundary points. This was a critical point on the boundary, and this was a critical point from before. And the values of all this is 72, this is negative 8. Oh, let me go back. I made a mistake, I guess. It was right here. This should have been negative 1. Negative 1. So I plug in negative 1 for x. This is a negative 4. Okay, so that should be 1. Okay. It's a negative 8, so I needed to correct that. Okay. And this is 224. And if I plug this in, I get about 3.7. And then when I plug that in, 0. So these two turn out to be local mins, but they're not the lowest. The lowest are going to appear at the boundary. This is going to be an absolute min because it's the lowest value. Negative 8's lower than anything, and this is higher than anything. So this is an absolute maximum because 224 is bigger than any of the other values. Okay, that's this how to find maxes and mins, local and absolute.